We call Cunsa our sound seasoning tool. Here is a quadruple mono or double stereo pingable multimode resonant filter, saturator, mixer, and oscillator. Ultimately, it is a filter, but we prefer to say that it is like multiple filters, and not just because there are 4 of them, but also because each filter can have completely different sound qualities or serve different purposes. Cunsa consists of 4 analog multimode resonant filters, each with its low-pass, bandpass, and high-pass outputs. All the filter slopes are 12 dB with the exception of the low-pass filter, which can be 12 or 24. On this side of the panels, we have some combined outputs for the 4 filters and some other inputs. These inputs here feature a series of semi-normalizations, so by patching a signal to any input, we will also feed all the inputs to its right. This is really what makes Cunsa more than 4 filters, but we will get to that in the second part of this tutorial. For now, we will see what a single filter looks like and what are its controls. All the filters are numbered from 1 to 4, from left to right. And so these inputs here refer to their corresponding filter. So this column refers to filter 1, filter 2, filter 3, and filter 4. These inputs at the bottom are clearly connected to the filters. Since all the filters are the same, let us start by patching a sawtooth to filter number 1 and patch the low-pass output to the CGM mixer, like this. Now we won't hear anything because the cutoff frequency is completely closed, so I will open it until I reach this state. You can hear that the sound is very quiet compared to the original sawtooth that we can patch here. And there is a reason to that we will see in a moment. The main parameters of a filter are the cutoff frequency, the input VCA, the Q knob, and the character. Input VCA and cutoff frequency are pretty self-explanatory. The Q knob is what in other filters is called emphasis or resonance, and it basically emphasizes the cutoff frequency, whether we are using a high pass, band pass, or low pass. We must rotate this knob to the right to increase the emphasis on the cutoff frequency point. The main feature of Cunsa's low-pass filter behavior is that even with high Q setting, you don't lose the bass content. If we reduce the input level, we will have an even clearer tone. If we increase it, the sound will be much tighter. Let us see how different Q settings impact the zone around the cutoff frequency on a 12 dB per octave low-pass filter. To do so, we measured how it changes the spectral content of a test noise. You can see that with low Q settings, the slope is very mild. The angle around the cutoff frequency gets progressively steeper. And at this point, we start seeing a resonant peak that gets progressively higher. The last parameter on the filter is labeled in gray, and it is the character knob. So we can drive the filter circuit by cranking the VCA all the way up. The character knob defines what the filter does when overloading. So by default, when it is set all the way to the left, it will have a sort of safety circuit that adds some soft clipping. It is very smooth, and we actually modeled it over the CGM. As we rotate it to the right, we are removing those safety circuits, and you can see that the filter is much more prone to overloading. Until we reach the furthest point, where we have the maximum filter saturation available. And so by combining different filter characters with different Q settings, we can obtain really different filter behaviors. Compare this very clean resonance to this much higher and screamy. And as we approach the fundamental tone of our sound, we might introduce a very loud distortion in the sound. Like this. We can try the 24 dB per octave. To clarify the character knob's behavior, let us take a look at what it does to a waveform through the oscilloscope. We are using a sine wave from the Brenso tuned to 1 kHz. The top waveform, the yellow one, is the original sound, and the bottom one in blue is the sound processed by the Cunsa. We are using the Q knob all the way to the left, and the input VCA is all the way up. The slope is 12 dB per octave. As we rotate the character knob, you can see that the waveform increases its amplitude in a nonlinear way, especially around noon, where it seems to be broken into some segments. Let us take a look at the 24 dB per octave low-pass filter. Let us see this nonlinear behavior also with a triangle wave. It becomes especially evident around noon and with 24 dB per octave. And finally, let's take a look at the sawtooth. Let us briefly compare a few settings of Q and character for the low-pass filter at 24 dB per octave, like we did with the 12 dB per octave. Also in this case, you can see how the character knob dramatically affects the overall amplitude of the sound passing through the filter. And to wrap everything up, I would like to show a graph that demonstrates the filter slope of both low pass 24 and 12 dB per octave with a character knob at its maximum level and different levels of Q. We will start with the minimum Q setting. The green line represents the 24 dB per octave and the orange line the 12. Then we have the Q at 9 o'clock. The Q at noon, and the Q at 2 o'clock. Let us hear also the other filter behavior, like the bandpass, with a Q and character setting like this. You can see that it is almost inaudible. And the reason is that it is the filter which is easier to make angry. Check out the difference with the character knob fully to the right compared to a more conservative but highly resonant bandpass filter. And the same goes for the high-pass filter. We start with a very mild 12 dB per octave high-pass filter. and we reach a much tighter sound with high Q settings. And now let us compare a few different resonance settings on the high-pass and bandpass filter outputs. You will notice that the bandpass filter is the most sensitive to resonance and character settings. Now, each filter has this switch here, which allows every control patch to the frequency knob, which here is labeled in yellow, to affect also the input VCA at the same time. So if I am using a very noticeable and colored filter in low pass filter mode, by activating the combo mode, I will reduce the amplitude in a nonlinear fashion as I go down. This creates a very organic decay, especially with the envelopes and with the ping circuit that we will see in a moment. But of course may create a bit of an uncanny sound with a high-pass filter. Because you can hear that as the filter opens up, the amplitude goes down, as opposed to the filter behavior that sounds like this. This can be very useful when we have very high Q settings, because it makes the transition very smooth. For example, like this. Instead of having a very raw behavior like this one. All those three parameters, cutoff frequency, Q, and character, are voltage controllable. As you can see right now, we are using this LFO to control the character knob, sample and hold to control the cutoff frequency, and a fluctuating random voltage to control the resonance. We can set another LFO and use it to control the input VCA, also voltage controllable. But when we are using a high Q setting and the filter is self-resonating, we can even remove the audio input and let it play by itself as a sine wave oscillator that we can control through the volt per octave input. And it tracks volt per octave pretty good. We can also try other filters as output, like the bandpass filter, if we want a different kind of sound. This is a bit more raw and harsh sounding. Let us take a look at the oscilloscope of what those waveforms look like. The filters are tuned to 1 kHz. This is the 12 dB per octave output. This is the 24. This is the bandpass. Notice how much rounded it is. This is the high pass. The filter design is the primary cause for this variation in amplitude and shape. We can use this knob here to fine-tune our oscillator. I'm giving you a free tip right now, because having these many sine waves that track this good with a true TZFM oscillator like the Brenso means that you can use Brenso as a double true TZFM oscillator, because every core is true zero frequency modulated. And so you can use two sine waves, patch them to the independent input, and boom, have two free complex oscillators. But let's go back to the Cunsa. The ping circuit acts as a non-linear integrator with a controllable decay time. The curve is custom, we designed it from scratch, and it basically integrates just the falling stage of whatever signal we patch into it. So for example, if we patch a trigger signal from Sapel, it will naturally create a sort of falling envelope whose decay time we can adjust like this. It is similar to Brenso's ping circuit, but this one is DC coupled, which means that it is sensible to different amplitudes and different durations. So, for example, we can use our LFO here from Falistri with its attenuated version to open it more or less. Or we can use a sample and hold like we were doing earlier and integrate just the falling stages. And this is where the combo mode really shines, because by setting this switch to the bottom position, we are now controlling with two slightly different nonlinear curves both the cutoff frequency and the VCA. It creates a very organic and natural decay, especially with FM patches. For the sake of clarity, I can say that there are two techniques that sometimes are called in the same way. One is filter pinging, which is what we just heard, and the other one that consists of patching a trigger signal straight into the audio input and then setting the filter very close to the self-oscillation point, but without exceeding it. And I have already covered this topic in another video that I will link here and in the description. This creates this very brief spike of self-oscillation. Now that we have covered pretty much everything that a single filter does, we can think about how to combine them together. So the first thing that we must mention is that every signal passed to either of these inputs here, either VCA, audio input, volt per octave, or ping, also feeds all the input towards its right in a semi-normal connection, which means that this signal, which is now going into filter 1, is going into filter 2, 3, and 4. So we are currently feeding 4 multimode resonant filters. And what if we want to listen to all of them together? Well, for this reason, there is the mixing section up here with these 3 outputs. This one mixes filters 1 and 2, this one mixes filters 3 and 4, and this one, all of them. Let's start from this one. We can see that now we are not hearing anything, so we have to gently raise those knobs for filters 1, 2, 3, and 4. Pay attention also to the VCA, because if we have a very low VCA level, filter 2, we won't hear it in the mix. But every filter, I would say, is multimode, so it has 3 different behaviors. And at a local level, it's easy to pick the one that we desired, but when we are using this mixed output, we must choose which of these outputs is going to the mixer. And for that, we have these 3 position switch here that let us choose between low pass, band pass, and high pass. So for example, we can set filter 1 to low pass, 12 dB, filter 2 to band pass, filter 3 to band pass, and filter 4 to high pass. And we can set the character and cue knobs so that they somehow match. We might set all of them to filter behavior, not to combo, and we can animate our sound like this. We can create some very interesting phasing effects. And if we didn't have enough gain, we can of course crank everything up with the color knob, with the cue, and even we can saturate the output stage like this. Since all these inputs are semi-normal, we can use an external CV, for example a DC offset from the 333, to control the amplitude of these filters, or just a few of them, for example these. And we can transpose all the filters at the same time through a dedicated offset, which becomes particularly interesting with low character and high Q settings like this. You can spread those filters out a little bit like this and create this very nice phasing effect. And of course, we can ping all of them at the same time, or maybe just a few. And perhaps use an LFO to modulate the first two. But in this case, our LFO is also feeding filters 3 and 4. So we may want to break the semi-normalization for these ones only. And if we want, we can take advantage of the separate outputs to listen to filter 1 and 2 on one channel, and maybe filter 3 and 4 on the other, stereo. This also means that if we want, we can use Cunsa as 4 independent filters, or maybe 2 couples. So we can feed the many different sources and control them with the same signal, or the other way around, using one sound with multiple control sources. There is another feature to discuss about the Cunsa, but for that I think it's better to put everything we learned today in a more complex patch. So right now we are using a Cunsa to process 4 different sounds, and we are taking the mono output of 4 filters straight out. And the first one is using the classic low-pass gate behavior that we can even accentuate through the combo mode. The second filter processes the same signal, but with a resonant bandpass filter controlled by Sapel's fluctuating random voltages. The third filter is processing this other waveform coming from Brenso's final output with a very slow ping here. And the fourth filter has a kind of a hi-hat sound obtained by pinging this low-pass filter here, fed with a white noise coming from Sapel, from this track on the Usta that uses some ratchets here and there. Of course, we can use the all output to bring all those sounds up together, like this. And the last feature that we need to discuss is the dry output. So we can mute our signal here and patch it straight to the CGM. It will give us a sum of the sound coming out of these VCAs before going into the filters. It is a bit quieter because we wanted it to have slightly more headroom, so making it not that easy to saturate, even if we crank everything all the way up. One thing worth keeping in mind about this output is that it is affected by the position of this knob here, and even if we use an external signal to modulate these filters, for example, if I patch an LFO here, I will affect all the filters at the same time, and so both the dry output and the mixed output will be affected. You can hear that this one is already saturating because I have some extra gain after the filters. Let's put everything to a more controlled level. Another thing worth keeping in mind as a consequence of this is that this output here is affected by the combo mode, because the combo mode modulates both the frequency and the VCA. So if I set my filters like this, you can hear kind of a pumping effect. You can hear the difference. So it is definitely something worth keeping in mind when you are using the all output, which might be a very interesting effect, especially if we want to use it to parallel process everything through Fumana. And we can combine everything together. This tutorial is meant to get you started with the Cunsa so that you can start using it in your patches. But it is a very flexible machine, and there might be way more uses for that, to which I will dedicate further episodes on this tutorial series. For now, I hope you found this one useful, and I will see you next time, where we will talk about how to get the most out of it.